Right, so we're going to look at another example of calculating the pH of a weak base titrated with a strong acid. So our first thing is let's check and see if we know what's even going on here. So we have a solution of weak base, we're adding strong acid to it. So what's going to happen? Well, we have a strong acid, nitric acid. So what that means is in an aqueous solution, if I could even type, that's going to completely dissociate. So we're going to have our conjugate base, the nitrate anion, which is going to be a neutral anion, and we're going to generate hydronium, okay? And that hydronium is what's going to react with and neutralize our weak base. Doesn't matter if we've never seen this weak base before, piperidine. All it matters is we've been told that it's a weak base, which means it's proton acceptor. So we can deal with that, right? So it's going to react. I should do it the same way around, NH, with our proton donor, there it is, right? Generated from our nitric acid is going to accept a proton. So I'm just going to stuff a proton on it, right? It doesn't matter if I've never seen this base before in my life. So NH2, and that'll get a plus charge, right? Plus water. That's literally what happens during a neutralization reaction. So one-to-one stoichiometry, yada, yada, yada. So we need to work out if we are before, at, or after the equivalence point to know how to deal with this. If we're before the equivalence point, then we're in the buffering region because the product of that neutralization is the conjugate acid of our weak base. That's literally a buffer solution. So what we have to do is we have to work out what the new number of moles of weak base and conjugate acid are just by subtracting off the number of moles of acid we've added and stuff those into the Henderson-Hasselbalch equation, or do an ice table if you want to have a sad life, right? Whatever, right? It's a buffer solution, we deal with it. If we're at the equivalence point, then we have to do an ice table based on the hydrolysis reaction of the conjugate acid with water. You totally know how to do that already. If we are past the equivalence point, then all the base has been neutralized and we just have an excess of acid. It's a strong acid, so all that matters is this hydronium, the H3O plus, right? So the way to work out where we are at is work out how many moles of each of the things we have. So let's start with this piperidine. We have 0.085 molarity solution. So I'm going to write that out as moles per liter. That's my little trick, right? So moles of base over 1 liter, and then the actual amount we have is 129.4 milliliters, and then of course that ain't gonna work as far as units go, so I've got to convert that milliliters into liters. 1 milliliter is 10 to the power of minus 3 liters, right? So that looks good. Calculation, that is 0.109. Oh, literally like the worst thing to have to to round, so I won't. Moles of my piperidine. Come see, come ça. All right, so we've done one. That's what we're starting with, and we've got to work out if we've added enough acid to neutralize that bad boy or not. Okay, so we're gonna have to take the concentration of our acid, which was 0.12 moles per liter, and the volume that has been added, where is it? Is much 1089.0. Again, you can't just go on the volume because they're different concentrations. Look how much more concentrated the base is. We're going to have to work it out. So I know, terrible, terrible life that we have. So 10 to the minus 3 liters, that'll work, and that comes out to be close. It's close. 0.13068 moles of nitric acid. Okay, so looking at the numbers, we have more moles of nitric acid that we've just added than we had to start with. That is more, yeah. Than we had to start with of our base, which means the base has been neutralized. Bye-bye. But we have excess acid, and it's a strong acid, so all we have to do to work out the pH is work out how many more moles of strong acid we have in excess, and then just do pHs minus log the concentration of the excess hydronium. So the moles of excess acid is going to be the moles of acid we added, which is 0.13068 moles, minus the number of moles of base added to neutralize. It's a one-to-one stoichiometry, so 0.10999 moles of the base. And we can go straight ahead and calculate the concentration from hydronium for that by dividing by the total volume, right? I guess I can just do this, right? Um, the total volume is all the volume of the weak base that we started with, so 129.4 milliliters plus we've added more stuff. So we have to add the volume of acid that we've added, and then moles per milliliter is no unit for concentration, so I'm going to have to convert that into moles per liter, which we can totes do. And that should give us our answer in terms of our concentration. Concentration comes out to be 0.01698 moles per liter of hydronium. Okay, it's a concentration. This is good. Let's just put some lines in there to guide our eyes so we know what we're doing. Okay. Liters cancels out moles per liter. So then all we have to do is our old friend pH equals minus log of the concentration of hydronium. Yay! So that was easy, right? So minus log of the concentration of hydronium, which we just worked out as 0.01698 moles per liter, and that comes out to be 1.77. So we get an acidic pH, which sounds reasonable because we've neutralized all the base and we just added excess acid. So at that point, we should have an acidic pH, and that's all there is to it.